Hello, thank you all for coming. It is my pleasure to introduce you Martin Schmid. Martin received his PhD at the Charles University on the topic of search in imperfect information games. He's a former research scientist at DeepMind Edmonton and IBM Watson, and now CEO and co-founder of Equilibra Technologies. His research deals mostly with algorithmic game theory and machine learning, but also other areas such as natural language processing. And he's one of the authors of DeepStack, the first computer program to beat professional players in no-limit poker. And today, Martin will present you Player of Games, a general-purpose algorithm for large, perfect, and imperfect information games. Which I feel fortunate to witness during my internship with Martin in Canada. And yeah, thanks. So Martin, thank you for coming. The word is yours.
Hey, thanks for the introduction. Can you hear me just fine? Thumbs up, Michal? Perfect. Okay, so yeah, hey everyone. It's good to see you, and it's good to be back in Prague. So I'm going to talk today about something we have done back in Edmonton, Canada, at the DeepMind office for the last few years, and that's going to be Player of Games. So let me just switch to the screen. So what is Player of Games? It's the first and general sound search algorithm that can play both perfect and imperfect information games. That's pretty much the short summary, and let's have a look at how it works and how we manage to do it. So on a high level, it's not like we couldn't play perfect and we couldn't play imperfect information games. There were algorithms like AlphaZero, which are really good at playing almost any perfect information game. It just learns to play the game through the general self-play method and learns some value functions. On the other hand, there are now algorithms for imperfect information games. For example, DeepStack. A few years back, we published DeepStack in Science, and we showed that one can indeed do search in games like poker. But these algorithms were both somewhat different. We had algorithms for two different classes of games, and these algorithms were quite distinct. So we all like general algorithms, the algorithms that do not really care about the domain in question. You just throw it out into the domain, and it learns to play the game or find a good policy in the environment simply by interacting with the environment. So can we do something about this schism? Can we design a single algorithm to rule them all? And one can indeed do so. And if you want to leave this talk in 5 minutes, you can do so now. And the short summary is Player of Games is a combination of AlphaZero and DeepStack. If you want to know more details about the combination, that's going to be the remaining, say, 40 minutes. And we are going to have a look in some details. Now, before we get to those details, even the story itself is somewhat interesting, because it tells us how it came to be, right? So a few years back, you might remember that we managed to publish DeepStack, and pretty much right after, we decided to join the newly opened Canadian DeepMind lab in Edmonton. Since we joined, it was quite natural for us to basically start working with the AlphaZero group, because AlphaZero was and still is an amazing algorithm, and it was also doing some games, except it was doing somewhat different class of games. And we decided, hey, how about we try to put DeepStack and AlphaZero together? That was pretty much the idea from start. So not only we got a chance to work with the amazing guys who implemented and designed AlphaZero, we also managed to build quite some nice collaboration with Prague's AI community over the years. and we managed to build this collaboration. So let me very quickly touch on this collaboration. Overall, over the years, we published before everything culminated in play of games. We published, say, about 10 papers, and a few of them we published in collaboration with Prague. You can see some faces that we work extensively over the years. And Michal also visited us in Bonn and spent a few months with us working as an intern in DeepMind. Even more collaboration and internships were planned, except travel and COVID made it quite difficult. But other than that, I think this was quite successful. So this is how play of games came to be. Let's now talk a little bit more about what play of games is, how it works, and what it really does, right? So before we can do so, before we can talk about the main ingredients of play of games, which is general search algorithm, we have to very quickly touch on offline solving. That is, if we have a game, what does it mean to solve a game? And traditional solution concepts are all based on offline solving. That is, you have a game, you somehow fit it into a computer, or you have some representation of a game, and then you solve a game. What I mean by that is simply you produce an optimal policy for each individual state of the game. You have a big table that says, okay, in this state, this is the action that you should take, and that's it. This is your solution. Then, given the solution, given your policy, you can inspect the policy, you can analyze it, and you can say, okay, this is how good the policy is, or this is how close the policy is to some solution concept of optimal policies. Now there are many popular concepts in the game class that we care about, which is to play zero-sum games. The concept of Nash equilibria or minimax solution concepts collapse and have some appealing qualities. But what I want you to take from this slide is you have some big tables, some offline policy, and you can then say, okay, this is how good the policy is. Now, search operates in fundamentally different settings, and we need to talk about it first properly. The components of search, if you were to think about how you would play, for example, chess, it's only natural to use search. You just think about a few situations ahead, and if you are too lazy or it gets too hard to search even further, you simply evaluate the situation at the end of your search. You look a few moves forward. You say, "Oh, I'm a queen ahead. This is probably a good situation." That's your evaluation. So it really is all about combination of two crucial building blocks, which is decomposition to individual subprograms, and then being able to somehow evaluate these subprograms for a value. This idea is not new at all, and it dates all the way to 1950s, where first papers and even first implementations of simple, say, chess playing programs were published and released. So all the ideas were already there. Now, as the time progressed, these algorithms got better and better, and I would say it all culminated recently with AlphaZero that showed that you can learn those value functions and have them be represented by neural network, and you learn all of this from self-play. That is, the algorithm doesn't really know anything about the game other than the rules, and then it plays the game until it learns a good value function, and that good value function is then used in a search, and it produces extraordinarily strong agents both in chess, Go, and other perfect information games. So search itself has been here for quite some time. It has some appealing properties, and there are now very general algorithms that can basically do search in perfect information games. When we wanted to build this general algorithm for perfect and imperfect information games, it turns out that that we couldn't really talk about what does it mean for a search algorithm to be sound or be correct in more general class of games, and that's there's a neat or interesting reason as a why. So as we have seen, or as we have discussed, these solution concepts were previously defined for offline policies. That is, you have a big table and tells you how to play in each state of the game. So if you were to look up a definition of Nash equilibria, this is where this solution concept lives, basically in offline settings. But how does search fit these offline settings? So on the very left, this is how it looks if you do search all the way to the end of the game. You have some state. You think about the state by simply looking forward, and then at the end of the game, at the end of the day, you produce a good policy for the state. If you add value functions, these simply just allow you to truncate your search and not to look all the way to the end of the game. And when you play a single game, you just collect your policies through the trajectory that you just visited, and this is your policy. So you basically only output a policy for the states you visited, not for all the possible states of the game, so that you can analyze it using the same methods that you can use for offline algorithms. Now, a natural idea is, okay, well, what if I ran my online search algorithm for all the states of the game, and then I can simply analyze how it plays? That's exactly how people think of it, and that's exactly wrong for imperfect information games. There are some interesting caveats, some things that are unexpected and break, and people do not really think about those things, because these things do not break in perfect information games. Basically, in perfect information games such as chess and Go, it's completely fine to say, okay, once I run my search, the policy for the currently visited state is good, in the sense there's some optimal policy for say for chess that would do the same action. So I'm good. My search algorithm is legit. My search algorithm is sound. Everything is good. The same argument breaks in more general class of games. So this is something that we all had to deal with from the very beginning. How do we design general search algorithm if already this is an issue? So one of the papers we published together with Prague, we actually had to define a new solution concept for online settings, basically an analog of Nash equilibria for online settings, where we then can talk about proper analysis of an online algorithm, and a similar concepts of epsilon closeness to Nash equilibria then also apply in these online settings. We defined a similar concept or related concepts such as consistency, where we can describe in what way or with what guarantees an online algorithm can play just like an offline algorithm in terms of worst case guarantees, which is exactly what, say, minimax policies are all about. So now we finally had proper ways to talk about these online algorithms. In imperfect information, the search, the components of the search that we just discussed, this decomposition and these value functions, these themselves need to be properly generalized. And this is something that DeepStack already did in a way, except that it only did so for poker. The question is this something more general? It turns out it indeed is. And it was relatively straightforward to generalize the idea of these subgames and subprograms for poker to more general class of games. This is again something that Prague started with and helped us to finish into a paper. And on a high level, all you really need is to talk about a combination of public states and distribution over individual private states. This is something that we will get into a bit closer in few more slides. What I really want to say on this slide is, in games like chess and Go, your subgame really is defined by simply the state that you currently see. That is your chessboard. In perfect information games, you also need, given a state, you also need a distribution over all the possible consistent states in a game. So for poker, you would need a distribution over all the possible cards the opponents could be holding. Or in games like Scotland Yard, you need a distribution over all the possible states Mr. X could be hiding. And that's basically the subgame. Value function in general always maps a subgame to its value. By value, I mean value under an optimal play. In chess, again, this is relatively straightforward. Your subgame is defined by a chessboard, and the game value is simply a value under an optimal policy of that subgame. The very same thing holds if you generalize it, except that your subgames are suddenly more general. You need the distribution that we just discussed. And the output of the value function suddenly is not just a single value of the subgame, but you also need a value for all those individual consistent states with the public information. When you basically try to do this using a neural network, it's relatively straightforward. The neural network as an input gets a tuple of public state or some features represented in the public state, and then a distribution over these possible player states, and the output is then a value for all the possible player states. So this is again relatively straightforward, except that the neural network architecture is then specific for a game. You probably want to use different architecture for chess and different architecture for Scotland Yard. Okay, now let's slow down a little bit again. When we generalized these concepts, or when we needed to generalize the concepts, we realized we don't even have a good language how to generalize them. And this became apparent quite soon from the beginning of the project. The issue being is the formalisms that were available to talk about these general imperfect information games. They have been here for quite some time, except that same thing again, they were only really useful for offline algorithms. Suddenly, when we needed to bring the ideas of AlphaZero into more general class of games and to properly define these concepts of subgames and value functions, the formalisms that were available since 1950s, they turn out that they are not really useful, or to say it even better, they were ill. It was impossible to define a search algorithm using these formalisms. So the formalisms that you would probably find if you were to Google for formalisms for imperfect information games, the first one you would find, the one that you would learn during your game theory one-on-one course would be matrix games. There's nothing wrong with this formalism, except that it's only useful for simultaneous move games. That is, both players act at the same time, and that's the end of the game. But many games are not really like this. Like even chess, you do want to make multiple moves during the play. And while it's possible to somehow represent these games using this representation, that's a really bad idea. Another formalism that is a lot more useful for the games in question is extensive form games, and that's a formalism that can indeed handle sequential decision making. It's just like a game tree that you are probably familiar with if you were to represent a game of chess on a computer, except that this formalism also somehow tries to capture the imperfect information. And it does so in a very simple way. It simply groups the states that are indistinguishable to the players, and that's it. You just group them together, and you call the resulting set an information set. Now, there's nothing wrong with this formalism if you want to use it in offline settings, and many algorithms can do so. Turns out that because of its simplicity, it's impossible to correctly define those individual subgames. Something that you can very easily do in chess. You just take your game tree and you find some small subtrees. Given this grouping, this definition of subtree gets very tricky. So at the end of the day, what we had to do together is to introduce a new formalism that has these modern search algorithms in mind, and we published factor observation as the stochastic games. It's a very simple algorithm that is based on stochastic games, and people that are coming from a reinforcement learning background would probably appreciate this formalism, because it's very much based on something that they are used to. You have some agents, the agents have some actions. After the agents make an action, the world moves to another state, a new world state, and everyone receives observation. The key thing that makes everything nice for search algorithms is that the observation is factorized into public and private observation. That is, each agent receives its private observation, and that's private, and the agent knows that it's private, that it's visible only to them. And there's also a public observation, which again, everyone knows that this piece of information is public. And the trick is, given that everyone knows that this information is public, then it's particularly easy to define this notion of public subgames and value functions working on top of these public subgames, because all you have to do is you group together all the states having the same public information, and the distribution that we need to define those subgames is simply distribution over all the different private things the players can know at that point. Okay, let's move to the next slide. Perfect. So these are the building blocks that we needed to do in order to build the player game itself. Now let's have a look at the resulting algorithm, the algorithm that managed to put together AlphaZero and DeepStack and create the first general algorithm for this class of games. And let's start with the inference. That is, let's assume that someone already gave us a good value function. It has already been trained. We just need now to use it in our search. So as we said, we combine DeepStack and AlphaZero, and the search is a perfect example of this combination. So what DeepStack used is it used this notion of limited lookahead search, where it used counterfactual get minimization to basically get closer and closer to an optimal Nash policy within its search tree. It's an iterative algorithm, and we basically had to go back and forth, visit all of the states in the search tree many times to basically converge to a good policy. Alpha 0, on the other hand, used a particular variant of MCTS. And MCTS on very high level, all it really does, it basically samples a trajectory in your search tree. Once it gets at the end of your search tree, Alpha 0 expands the search tree, evaluates the new leaf node using its value function, and that's it. It just keeps doing this. Now there's a very important thing that's that's necessary for perfect information games, and that's the expansion. That is, Alpha 0 is able to expand its search tree where it's necessary. That is, if say you play chess, you will also probably think a lot more, or you will look more actions forward when you believe that this particular trajectory is more relevant or important. And that's exactly what Alpha 0's MCTS allows. It basically, as it thinks, the search tree gets larger and larger. Now, on the other hand, MCTS nor any of the variants that you can find, they do not work in imperfect information games. Even if you can basically hack together MCTS so that it doesn't crash in imperfect information game, it's still not going to converge. And in the appendix, we also show some results of MCTS failing to find a good policy in small imperfect information games. So now let's put it together. Can we somehow use the regret minimizer of DeepStack and still expand its search tree using Alpha 0's MCTS like ideas? And yeah, the answer is yes. And the high level is relatively simple, except that there are many tricky details that we will not go into. But on a high level, the algorithm of player of games that we use during the search, that's something that we call growing tree CFR, and the algorithm combines two phases. It's the phase of policy optimization or regret minimization. That's very similar to to DeepStack, and the phase of tree expansion, which is again similar to Alpha 0. So for the regret minimization phase, that's almost identical to DeepStack, except for some distinction in how we do continuous solving to make sure we handle more general class of games. But other than that, it's just like our DeepStack did. The expansion phase, that's somewhat more tricky, because while the regret minimizer and the search tree operates on top of these public states, the simulation that's inspired by MCTS, that's been run on individual world states, that is individual histories. But once we get at the end of the search tree, we still need to expand the public tree. Again, this is the more details are in the paper, but on a high level, you can think of as two phases being intertwined, where the MCTS basically expands your tree, and then you use CFR to improve your policy in the search tree. And the cool thing is, while it's not easy to prove, we can still bound the overall regret in the search tree, and that's despite the fact that the tree gets ever larger, right? Like what DeepStack previously did is we could bound the overall regret in the game because we had a fixed size tree. Player of games can still bound its overall regret and basically the quality of the resulting policy, even though that the regret minimizer basically runs as often as the tree expansion. So even if you run one CFR iteration and then one expansion and then one CFR iteration and you went back and forth, even though the tree gets larger and larger, you can still bound the overall regret. Now, this was all fine and dandy, but it was assuming that someone gave you a good value function to be used in this growing tree CFR algorithm. How do we actually train this value function? So the thing to think about is, how do we cover the state space of the relevant subgames? What we know is that the value function needs to tell us something about the subgames. It needs to produce correct values for these subgames. But the space of all the possible subgames is way too big. In chess, it's huge, but it's still finite. There's only a finite number of chess situations. In imperfect information games, because the subgame is also defined by this distribution over all the possible private states, suddenly this all explodes, right? Like how can you basically cover the space of all the possible distributions in all of these public states? What DeepStack did was more or less we covered the space simply by sampling from this distribution of all the possible subgames, and then we learned a neural network, and the hope was that the neural network will generalize well. That's fine as long as you can define your sampling distribution, and in the case of DeepStack, it was more or less hand-tuned for poker. But we want an algorithm that's not hand-tuned at all, right? We want an algorithm that just, you give it a game and it just learns to play the game. It just learns this some distribution of subgames and values and trains a neural network on it just from self-play. That's what AlphaZero was able to do, and that's what playoff games can do now as well in this more general class of games. And the idea, I think, is relatively neat and straightforward once you understand it. And the idea is simply this. So the relevant subgames that you want your value function to be good at are the subgames that you encounter during the search. As you search, you basically ask your neural network for, hey, give me a value of this subgame. So every single time we call a neural network, we call this input a query. So we query in a neural network for a subgame value, and we want our neural network to answer well those queries asked during the search. So we collect all those queries visited during a single self-play trajectory. Then in the next step, we somehow need to find a good values for the neural network, so that we can train our neural network almost as in supervised settings to learn our neural network to predict well the correct values. Of course, the ideal target is the subgame value of those queries, but this is impossible to compute, because again the subgames that you encounter during the search are still going to be humongous. But we can do the second best thing, and that is we will approximate the values. And the trick is we can approximate the values using the very same algorithm, the growing tree CFR, that we use during the self-play, except that during the self-play we use the growing tree CFR to basically find us a good policy, so that we can play our self-play method. While when we are trying to find a good value for our query, we use the growing tree CFR more as a solver, where we still run the CFR and expand the tree. But at the end of the day, we do not really care about the policy. We just care about the value at the root of our search tree. You can it's the same thing if you were to run minimax, right? Like if you run minimax in chess, you can either care about the policy in your root node, or you can care about the value in your root node. So that's more or less how we find the values. Now there's another neat idea in this approach, which is, as you are using this growing tree CFR to also learn good target values for your queries, the search procedure itself will create yet another set of queries, right? And this is something that we call recursive queries, and the process on the picture that's B basically continues. And if you do this properly, if you take care of those recursive queries well, then you can show another neat theorem. This is despite the fact that the state space of all the possible subgames in a game is way too big. If you do this procedure if you do this properly, even in finite amount of time, you will basically encounter all the relevant subgames that you need in order for you to converge to basically epsilon Nash equilibria. In a sense, say someone tells you, okay, I want you to be as close to Nash equilibria as if you ran, say, 1000 CFR iterations. There's a number of steps in this process that's finite, that basically covers all the possible subgames that you need to learn about. And while the result is somewhat impractical in the sense you will probably never have a neural network that has the same memory power that you would need, it's still an interesting and neat theoretical result. So this is what happens if you basically start this self-play method from scratch, and you run it, say, on a small poker or a small Scotland Yard game, small enough so that you can then properly evaluate how well your algorithm plays. And we already talked at the very beginning that we can now properly evaluate those search algorithms, and we can say, hey, this is how close to an optimal policy it is. So you can see that at the very beginning, the algorithm starts with a very poor value function, poor neural network. So it more or less plays randomly, and it's very far from an optimal policy. But as the training procedure that we talk about keeps going, the value function gets better, the self-play improves, that on the other hand produces another set of queries that are more relevant, the value function again improves, and this self-improving process keeps going until we basically converge close to an optimal policy. Now, the cool thing to see here is that the agent is limited by two things. Basically, the quality of the neural network, that's something that gets better and better as the x-axis goes. And also by the amount of search that you do during your search procedure. And that the amount of search that corresponds to different colors on these pictures. And as you can see that for all of the colors, as your neural network gets better, the agent gets closer and closer to an optimal policy, but then it plateaus. But the plateau very much depends also on how much search your agent does with that network, and that's something that you can exactly measure in these small games, and that's something that exactly our theorem suggests. So that's pretty cool to see this confirmed on our small games. Now let's finish with the results on the large game. That is not only we managed to design the algorithm formally, implement it on small games, but if it's general, then we can also do big games, except that we cannot evaluate them in the sense of how close are they to optimal policy, but we have other methods to evaluate the large games. And the large games we decided to basically tackle with these algorithms were two perfect and two imperfect information games to really show its generality. So in here we have poker and Scotland Yard for imperfect information games. If you do not know Scotland Yard, I don't think I have time to explain it other than please go and Google it if you are curious. It really is a graph chasing game where you have a graph, you have some stones, and you are trying to chase down another stone, except that you do not really know the exact location of the stone on the graph. You rather have to infer somehow or form a belief about its location based on the actions that are observable too. So there's a cool photo that's, I mean, that's something that you find if you Google for Scotland Yard. So you can think of detectives trying to chase down chase down someone. They do not really know where the person is hiding, but they just have some clues about their location. And for perfect information games, we chose chess and Go because what other two games to choose? So how well did it work for perfect information games? It worked the way we expected and hoped, in the sense as this is algorithm that's general. It's not as strong in perfect information games as AlphaZero, as AlphaZero is specifically designed to shine in perfect information games, and it's extraordinarily strong there. The playoff game is all about generality, in the sense we wanted to have a general algorithm that's really good in basically any game, with some caveats. We will come back to what any means, but we want something that's really good, ideally superhuman, which we believe this is by far better than any human. But we are not that worried that there are algorithms that are specifically designed for some subclass of games, and we are behind. So these are the relative ELO numbers between AlphaZero and DeepStack. As for imperfect information games, they were the same story here. Even though evaluation of imperfect information games is a bit more tricky, the POG is still extraordinarily strong. It still has a good exploitability approximation from a local best response, and it's it's beating the previous state of the art in Scotland Yard, regardless of how much time we give the other agent in Scotland Yard. So now it's ideal time for questions. I promise that I will leave 20 minutes for questions. So yeah, thank you.
Thank you very much for the talk. So if there's questions.
Yeah, thank you for the presentation. So I'll just start with a quick question. The paper says something about like 3,600 TPUs or something that insane. So was it actually necessary for everywhere, or was it just that you had it, so you used it?
Yeah, I think it's more the latter, in the sense that Google has a lot of TPUs, and it's easy to get lazy sometimes. Rather than optimizing or running on less TPUs, you get lazy and you run on a lot of TPUs.
So how, like, was it that you just computed everything on this amount in a few days, or like what is could this be replicated like at a university setting where you can have like a machine with 4 GPUs?
So Scotland Yard and poker, I think easily. Chess, I think you can replicate with some reasonable number of GPUs. With Go, Go is hard. Like even the AlphaZero over the years got really good in getting chess and Go results with a lot less compute. So if you wanted to get a really good chess and Go agent with something like playoff games, the most recent AlphaZero agents need say an order of magnitude less compute than playoff games. But it's simply because we never really cared about it.
Thanks.
So I'll ask. So can you elaborate more on that any game?
Yes, thank you. No, that's a perfect question. So player games can play quite a general class of games, but there are some fair limitations. And I think by far the biggest limitation is that as we were talking about these public states and value functions, your value function basically needs as an input distribution over all the player states in a public state. Now, in some games, this is there's one state. In some games, there's 1,000 states. But there are some games where this number just explodes again, and that's something that playable games cannot deal with at all.
Okay, thank you. So a natural question: what are your views on solving that problem?
I think that's a question for Michal, because he.
Like, I know, but I want I want your input because his views can be biased. So
yeah, so my view is basically every single time you have too many things to deal with or to represent explicitly. Right? This is the issue. You cannot represent explicitly all the possible private states. Then you can either represent them implicitly, which is a good idea if you can find some good implicit representation, or you have to sample. Michal chose the sampling path. I think the implicit representation is the other one.
okay, thank you.
I have a question. So player of games is very similar in some sense to AlphaZero. And so you had a plot with the numbers on Go, like there's some gap, and this is because player of games is more general, so it's understandable that the performance is lower. Have you tried to run some kind of ablation study to see like what are the components that you would need to like basically could you like scale like by turning off some of the components to get like pure AlphaZero on as like some kind of parameter tuning, like if it's 0 you have AlphaZero, if it's 1 you have player of games, and try like doing some kind of ablation study, like what is the most important differences?
So this is a nice question, and I would honestly also like to know the answer to it, right? Because if you run play of games on perfect information games, there are few things that are different to how AlphaZero does it, right? Like one of these being the counterfactual radius minimization, versus the AlphaZero MCTS, but the other one also being you still have to do the continuous solving and gadget, right? So it would be interesting to see which pieces are the ones that that basically hurt you. And sorry, I don't know. Question. There's a question in the how do I open this? More chat. But it's also. Okay, yeah, so we have I'm going to read the question so that it's recorded. You said that MCTS is not suitable for imperfect information games, but there is also POMCP, partially observable Monte Carlo planning, which extends MCTS to partially observable domains. Would POMCP be suitable to use instead of CFR? Did you have a look into this? Okay, so thanks for the question. So one of the agents that we evaluated against in Scotland Yard, or the only one really that's the state of the art up until play of games, was based on basically partially observable MCTS. That algorithm is exactly MCTS that does not crash in imperfect information games. You can implement and run it, but it has zero guarantees in the sense that even in very small imperfect information games, it's not going to produce an optimal policy. So that's a huge difference to play of games, which has very strong theoretical guarantees.
Can I have one question also?
Sorry?
Can I have one question? The counterfactual value network has kind of fixed input and output, do you think that future like research could be that the output would be kind of like a sequence for each information state together with kind of mu0 abstraction of the game, so you don't have to use simulator?
I see. Okay, so yes, that's a valid point. So the mu0, which is one of the latest variants from the AlphaZero lineage, doesn't even need a simulator in its search, and that's something that I can imagine playoff games being extended into, basically not needing the simulator. And yeah, I know we already talked about this. I'm not sure if that's going to be the first thing how people will try to generalize playoff games, but it's certainly an interesting path, and I think it's doable.
Thank you.
Okay, I might have one more question then. Like there is this line of work with search, and then there is AlphaStar and these like more multi-agent reinforcement learning approaches. So do you have some more clarity on when we need to do search and when we don't, or how to choose which way to go in domains like this?
Yes, no, thank you for the question. So basically the other line of the work, the non-search one, I think it's fair to say that most of it is based on a PSRO family or PSRO ideas in the sense that use some learning or reinforcement learning methods to build your high-level policies, and then you mix between them. The way I think about it in say, for example, StarCraft, I think you can still play very, very good StarCraft if you find few really good high-level policies. Say you either rush or you do this or you do this. You have some number of really good policies, and then you just mix in between those. While even though this might not be optimal, playing small support with some small number of neat policies, that's still going to be really, really good. So yes, I'm a lot less skeptical about those approaches now. But the thing that you are really asking is, when do we need search and when we do not need a search, right? And I don't really have a great answer, other than that it's interesting that people do not ask this question in perfect information games, or I haven't really heard this question often in that community, but it's quite prevalent in imperfect information games. So there must be something special in imperfect information games that makes people to think about it, and maybe the main reason people ask this is, wait, search is hard. Why do we have to do search? But in perfect information games, very few people would argue for offline policies. Or I mean, I'm actually curious what your view is.
So my view is that like the search always helps. It looks like if you can do it, even in your experiments, like I like the nice results that it looks like if you can do more search, it helps. So I see the future in a combination of the things, that you would create offline something like AlphaStar, which would create a policy, and then you could use this policy locally and improve it using some Monte Carlo search. I think that would work. So I'm actually not sure whether it's necessary, like how much you would be able to improve it. But definitely in some domains you probably can improve it. In others, I don't know. Like I would actually be interested in a project where people would try to apply AlphaStar really proper to things like poker and really see whether it's possible to get similar results or not, but it might be possible.
Mhm.
So I'm not an expert, but I was wondering, when you have all of the theory, can you really do only with the TD0? Or do you need to go like sort of a deeper in the tree?
So the theory holds even with just TD0. You just the argument being is if you do TD0 for long enough, the values will bubble up all the way up. In practice, doing something more aggressive probably helps, because this is something what AlphaZero I think have seen in perfect information games as well.
Mhm. Thanks.
Are there any other questions?
I maybe wanted to verify if I understood it correctly, that during the iterations of player of games, you maintain a public tree, right? And then the query buffer or replay buffer for training the network and the network, right?
Mm-hmm.
Yeah, okay, thanks.
Maybe I just had a quick question. Lately in machine learning, there's been for computer vision and so on, there's been a lot of focus, or like methods that use self-supervision have been shown to be quite strong. Do you think something like this is useful for value functions? Or it's not something that would benefit too much, as perhaps like the inputs are very like well defined compared to like natural images and so on, where you have to extract actually the useful signal?
It's not like I haven't thought about it, because the self-supervision results recently have been extremely impressive, right? Like the I follow closely, for example, the Fair group from Facebook, and many other places. They've shown that that self-supervision, when done and scaled properly, can almost do magic. So yeah, I also thought about it, and I mean I don't know, other than the current models that we all use for value functions are quite basic compared to what the self-supervised people are using, right? They have these humongous transformers and everything. Most of our value functions are just feed forward, or at most ResNet. So maybe a lot of the magic could also be gained simply by doing more fancy deep learning, which we are not doing. Okay, there's one question in the chat, which is harder to go or Scotland Yard. Yeah, so definitely Go is really tricky to learn, and we need a lot of compute, and we needed a lot of time to tune the neural net architecture before we managed to get some reasonable ELO. Awesome.
And maybe like last question from me, have you tried to play against like have you tried to play on these games like Go or chess against your own algorithm?
Yes, I played chess, and I mean I'm not a good I'm not a very good chess player, and this agent could beat even a very good chess players. But it was still fun. Like that's an experience that you don't often get if you actually play against an agent that you designed. That's super fun. Awesome, thanks.
Okay, so thank you for the talk, and yeah, thanks for coming.
Thanks everyone. Have a nice day.